Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
Today's lecture concerns the emergence of topology from quantum mechanics. It is divided into 5 parts. First, we explore the Berry phase, where quantum evolution acquires a geometric memory. Second, we discuss spectral flow, the smooth shifting of energy levels as external conditions change. Third, we introduce the famous Aharonov-Bohm effect, where quantum particles sense magnetic flux without encountering a magnetic field. Fourth, we examine a Hall system in a ring geometry, subject to the influence of an Aharonov-Bohm flux threading through the center. And finally, we address Hall conductivity on the torus and its deep connection to topology through the first Chern number. Join us as we uncover how topology, a concept once rooted purely in mathematics, emerges naturally from the quantum fabric of reality. Berry phase. First, imagine a quantum system. It depends on internal variables and also on external physical parameters. The system's evolution is described by the Schrödinger equation. Now, suppose the system starts in its ground state, the state of lowest energy. We slowly change the external parameters, moving around a closed loop in the space of possibilities. As we move, the ground state itself changes smoothly. According to the adiabatic theorem, if we vary the parameters slowly enough, the system will stay in its ground state. It can only pick up an overall phase, a real physical shift in the wave function. If we assume the ground state energy is 0, we can focus purely on this phase, without any dynamical effects. By following the evolution carefully, we find that the system's phase shift is governed by something called the Berry connection, a mathematical object that measures how the ground state twists as the parameters change. Over a full loop, this twisting accumulates into the Berry phase, a geometric memory that depends only on the path taken, not on the details of how we moved. This phase is robust. It is independent of arbitrary choices we make in defining the system's state. Ultimately, the Berry phase reflects a hidden curvature in the parameter space, a beautiful signature of geometry in quantum mechanics. Spectral flow. Let's walk through an important example, spectral flow. Imagine a solenoid, a coil of wire carrying a magnetic field inside it. The magnetic flux through the solenoid is called phi. Outside the solenoid, there is no magnetic field, but the vector potential is not 0. This hidden influence affects quantum particles moving around the solenoid. Using Stokes' theorem, we find that the vector potential around a circle of radius r is proportional to the magnetic flux phi, divided by 2 pi times r. Now, think of a quantum particle moving on that circle. Its Hamiltonian, the operator describing its energy, depends not just on its motion, but also on the magnetic flux. As a result, the energy levels or spectrum shift depending on the value of phi. If phi is an exact multiple of a fundamental quantum of flux, called phi naught, then the spectrum looks the same as if there were no magnetic field at all. But if phi changes by 1 quantum, each state shifts, n becomes n plus 1, while the overall spectrum stays unchanged. This phenomenon is called spectral flow. However, something special happens when phi reaches half of a quantum. At this point, energy levels cross and degeneracies appear. Because of this, the adiabatic theorem no longer holds. In the end, even though the magnetic field is confined inside the solenoid, its effects are still felt by particles outside, a striking demonstration of the hidden geometry of quantum mechanics. Let's now explore the Aharonov-Bohm effect, our first physical realization of the Berry phase. The key idea is this. In quantum mechanics, the Hamiltonian, the energy operator, depends directly on the vector potential, not just the magnetic field. Even though the vector potential is not directly observable, it still influences the quantum particle. This is in sharp contrast to classical physics. Now, imagine a quantum particle trapped in a tiny box, centered around some point in space. At first, the box sits where the vector potential is 0, and the particle's wave function is simple. We then slowly move the box along a path to a new position. As we do this, the wave function accumulates a phase, a memory of the vector potential encountered along the way. By carefully solving the Schrödinger equation, we find that the particle's wave function picks up an overall phase, proportional to the integral of the vector potential along the path. When the path forms a closed loop, the accumulated phase depends on the magnetic flux enclosed. This is the Aharonov-Bohm effect. Here, the Barry connection is none other than the electromagnetic gauge connection, the vector potential itself. Thus, even when no magnetic field is present along the particle's path, the hidden geometry of the field leaves a real, physical imprint on the quantum system. Hall system in a ring geometry in the presence of an Aharonov-Bohm effect. Let's now turn to a new setup, the Hall system in a ring geometry in the presence of an Aharonov-Bohm effect. Instead of an infinite plane, we imagine the Hall system placed on a ring. This allows us to include not only the background magnetic field, but also a magnetic flux threading the center of the ring. The Hamiltonian for a charged particle in this setup contains two parts, the kinetic energy modified by the magnetic field, and a potential that can represent disorder. For the uniform magnetic field, we use a symmetric gauge where the vector potential points tangentially, growing with the distance from the center. In polar coordinates, the vector potential has only a phi component, proportional to the radius. The particle's momentum is modified accordingly. Now, an additional magnetic flux is introduced at the center, the Aharonov-Bohm flux. Although the magnetic field associated with this flux is zero inside the ring, the enclosed flux still affects the wave functions and energy levels. The Hamiltonian now includes this extra flux. The structure becomes slightly more complicated, but its effects are profound. Several important observations follow. First, the Hall magnetic field is non-zero inside the ring. Charged particles feel a Lorentz force, leading to cyclotron motion and the usual Landau levels. The magnetic field can be described smoothly by a single vector potential everywhere. Second, the Aharonov-Bohm flux introduces topology. Even though the magnetic field from this flux is zero, where the particle moves, the space is now multiply connected. There is a hole in the middle. This prevents defining a smooth global vector potential, creating a non-trivial Barry phase when the wave function circles the flux. Third, the key difference between the two fields, the Hall field and the Aharonov-Bohm flux, is that the Hall field can be globally described by a smooth vector potential, while the flux cannot. The Aharonov-Bohm effect is purely quantum and purely topological. Now, what about the states? The Aharonov-Bohm flux affects only the extended states. Localized states, those confined to small regions, are unaffected. This is because extended states wrap around the ring, making them sensitive to the topology, while localized states do not encircle the flux and thus feel nothing. For extended states, a gauge transformation trying to remove the flux fails unless the flux is an integer multiple of a fundamental quantum. Thus, for extended states, the flux is a real physical effect. Next, spectral flow. Suppose we slowly increase the flux. As the flux grows by one quantum, each extended state shifts smoothly into the next. If the potential disorder is zero, the system is clean. In this case, the wave functions in the lowest Landau level are simple, localized around specific radii depending on their angular momentum. As the flux increases, each wave function moves outward. An electron is effectively transported from the inner edge of the ring to the outer edge. If multiple Landau levels are filled, multiple electrons are transferred. This process generates an electromotive force, a radial current, and defines the Hall resistivity. Even in the presence of disorder, the picture remains similar. The number of extended states is reduced, but there are always at least two, one near the inner edge and one near the outer edge. Spectral flow still shifts these states, transferring electrons across the ring. Thus, whether the system is clean or disordered, slowly increasing the Aharonov-Bohm flux by one quantum causes a net transport of electrons, a beautiful demonstration of topology, quantum mechanics, and geometry all coming together. Hall conductivity on the torus and the Chern number. We now move to a new setting, a Hall system placed not on a ring, but on a torus. Imagine starting with a rectangular sample. By identifying its opposite sides, we fold it into a toroidal shape. Another way to think about it, we connect the inner and outer edges of a ring. As a result, the system becomes periodic along two directions, with lengths L1 and L2. In this geometry, we consider a uniform magnetic field pointing perpendicularly through the torus. To describe motion in this setting, we introduce magnetic translation operators. They are built from the momentum and the vector potential of the magnetic field. Without a magnetic field, translations simply shift the particle along the torus. But when the magnetic field is present, translations pick up an extra phase, depending on the vector potential. Using the Landau gauge, where the vector potential grows linearly along one direction, the wave function obeys periodicity conditions, but only up to a gauge transformation. When we follow a full cycle around the torus, consistency demands that the phases match. This leads to a famous condition, the Dirac quantization condition. It states that the total magnetic flux through the torus must be an integer multiple of a fundamental unit. Next, we introduce two fluxes, one threading through the x direction and another through the y direction of the torus. These fluxes modify the gauge field and induce spectral flow. As the fluxes are varied slowly from 0 to 1 quantum of flux, the wave functions smoothly transform into each other, even though the overall energy spectrum remains unchanged. Changing the flux over time generates an electric field. This creates a perturbation in the system, proportional to the electric current and the applied flux. Using first-order perturbation theory, we find how the ground state of the system shifts with respect to the applied fluxes. This obtained result, in conjunction with the celebrated Kubo formula, relates the Hall conductivity to the sensitivity of the ground state wave function under changes in the applied fluxes. The Hall conductivity turns out to be related to a Berry curvature defined over the space of fluxes. Now, because the fluxes are periodic, increasing by one flux quantum brings us back to the same physical situation. The space of all possible fluxes is itself a torus. We call it the flux torus. We represent the fluxes using normalized angles. Thus, the space becomes two-dimensional and periodic, just like the physical torus. The Berry connection and Berry curvature are defined over this flux torus. The Hall conductivity is proportional to the Berry curvature. More precisely, it is proportional to the integral of the Berry curvature over the entire flux space. This integral defines the first Chern number, a quantity that is always an integer. As a result, the Hall conductivity is quantized, reflecting the topological nature of the system. When we vary the fluxes around a closed loop in flux space, the system accumulates a Berry phase. Using Stokes' theorem, this phase is related to the integral of the Berry curvature over the enclosed area. If we integrate over the entire flux torus, we find that the total Berry phase must be a multiple of 2 pi. This leads to a remarkable result. The first Chern number is always an integer. Thus, the Hall conductivity is quantized, a hallmark of the integer quantum Hall effect. The relation between the first Chern number and the quantized Hall conductivity is known as the TKNN invariant. This topological quantization is not a property of the material alone. It reflects the deep geometry of the quantum system, a discovery that changed our understanding of condensed matter physics forever. This brings us to the end of today's lecture on the emergence of topology from quantum mechanics. We explored how deep mathematical structures naturally arise in the quantum world. Thank you for watching. If you enjoyed this exploration, consider subscribing to Quantum for more deep dives into theoretical physics. Until next time, keep questioning, keep exploring.